So, last class we were having a look at this relationship between the angular momentum of a rigid body at about a point A, about point A, and with respect to frame F. So this is the rigid body here, and this is the frame F. Now this point A is fixed to the rigid body, and only when A is fixed to the rigid body you can write a relationship like this, what I have, that the angular momentum of the body equals a dot product. In the dot product, the second factor is the angular velocity of the rigid body with respect to F, and then we introduced a new quantity which is called the inertia tensor of body M at point A, which is a second order tensor. Now this can be derived, this relationship can be derived. However, I have not discussed the full derivation in the class. I will upload it on Moodle, the full derivation, but that will not be part of any exam on this course. Okay. Now note that this order has to be maintained. This dot product of the second order tensor should be such that on the left hand side you have the inertia tensor of the body at point A, and only on the right hand side you get omega mf. Mind you, this is not the same as this. If you want, you can show this. Last time I explained how a dot product between a second order tensor and a vector to be taken. If you follow that rule and try to find this on one hand and try to find this on the other hand, you would observe that these two are not the same quantities. Earlier, when the participating quantities were both vectors, we are very well aware that A dot B is B dot A when both A and B are vectors. This we have seen for a long time. Even in your school days you must have seen this, even in 10th class. But mind you, once one of the tensors becomes a second order or a higher order tensor, this is generally not true. Generally not true. Generally not true. Okay. So we should stick to this order. Okay. Then in the last class itself, I tried to perform this dot product operation between this tensor, second order tensor, and the vector, and I used a Cartesian coordinate system for this operation. And this Cartesian coordinate system was such that, it's all recap, I have done all these. I'm just trying to help ourselves remember what we did last time. So the Cartesian coordinate system that I am using is this. a origin of coordinate system. Okay. If I use such a Cartesian coordinate system as my working coordinate system, then I showed that this equation relating the angular momentum to inertia tensor and the angular velocity vector can be written as a matrix product or a matrix multiplication. Left hand side I have h1, h2, h3. These are the three scalar components of the angular momentum in that coordinate system, which I showed on the last slide. h1, h2, h3. Omega 1, omega 2, omega 3 likewise are the three scalar components of this vector in that coordinate system. And then this 3 by 3 matrix that is appearing here is the matrix of, or the collection of, all the scalar components of the second order tensor in the same coordinate system. Recall, I told you in the last class that once a tensor is second order, you need to have 9 scalar components to express that tensor in a coordinate system. Those are the 9 scalar components of inertia tensor. So when it is a vector, there are 3 scalar components and we need only one index, omega 1 or omega 2 or omega 3, to denote the scalar components of a vector. But when it becomes a second order tensor, you need 2 indices to specify which scalar component you are talking about. So you can have a component as IA11, IA12, IA13 and all the way to IA33. 9 scalar components, and those 9 scalar components indeed are appearing as a matrix here, right? So this matrix expression can be written in a more compact form as I have written here. So once I put the square brackets, what I mean to convey is that I am talking about a matrix now. Matrix. This is the matrix. This is one 3 by 3 matrix. This is 3 by 1 matrix. This is 3 by 1. Every time I don't want to write all this thing. Instead, I will write like this. Okay, in a more compact manner. Now this matrix equation represents 3 scalar equations. 3 scalar equations. These are the 3 scalar equations. One equation for h1, another for h2 and another for h3. h1 is this. There is a pattern here. You can easily pick up that pattern: IA11 omega 1, IA12 omega 2, IA13 omega 3. So the pattern is that these indices are matching, whereas this index is matching with the first index of I here. So 2 is matching with 2 here, with 2 here and 2 here, whereas these indices are matching with omega. Same thing here. 3 and then 1, 1, 2, 2 and 3. All this follows from the way we defined the dot product between a second order tensor and a vector. Alright. Continuing with the same idea, matrix representation of this equation, I am summarizing that this matrix that is appearing here, we would call this as the inertia matrix of the rigid body in context. At a point A, and relative to the coordinate system ax1 e1 x2 e2 x3 e3. That's the coordinate system I have here. Okay, so there are three things. Whenever you see a matrix like this, there are three things. It is the inertia matrix of an RB, and that should be clear from the context, at a point A and relative to the coordinate system given here. In contrast, remember this quantity, when I do not put any square brackets, it's just IA double bar. This is the inertia tensor of RB at point A. Inertia tensor. Once I put the square brackets, I start calling it inertia matrix of point A and relative to coordinate system. Here there is no reference to any coordinate system. No reference to any coordinate system. The tensor itself is independent of coordinate system. It's just like the vector, right? There is a vector going from Earth center to the Sun center right now. Do you need a coordinate system to define that vector? No. That vector is independent of the coordinate system you choose. Similarly, this is a coordinate system independent quantity. But once you start using a working coordinate system, it will show its 9 scalar components, and the collection of those 9 scalar components is represented by inertia matrix of the RB at point A relative to the coordinate system that you have chosen. Keep this in mind. Now moving on. So all that was a recap. I just copy pasted the slides from the previous lecture. Now we move on to a new material. Mathematical definition of IAIJ components. IAIJ components, where I is going from 1, 2, 3. I mean, it can take values as 1, 2, 3. J can take value as I 1, 2, 3. So what is the mathematical definition of these components? You would realize that the way I presented this material to you in the last class and today, I have presented so far I have presented inertia tensor as a quantity, as an entity, and I have talked about its scalar components only symbolically. IA11, IA12, only symbols I am using. After all, what is the mathematical definition? The mathematical definition of various components are as follows. I'm going to write them now. So I am writing this matrix, IA double bar this. So the first scalar component, which we denoted as IA11, that equals this. So again, what is dm? Dm would be a small mass here on the body. Dm is part of the RB, which is M. And then you will go and look at its centroid, say P. So P is a generic point, a typical point. It has coordinates x1, x2 and x3. Right? And in the neighborhood of that P, you take a small chunk of mass. dm is a small chunk of mass in the neighborhood of point P, where P is part of RB and it has coordinates x1, x2, x3 in general. Like before, A is part of RB also. Okay, so this is the integral x2 square plus x3 square dm over the entire body. That's what is IA11. Again, if I had shown you the full derivation, this would have appeared naturally. But in this class, I am presenting this matter in a different way. I am not giving you the full derivation, I am giving you the expression itself directly. And the reason I am not giving you the full derivation is because I wanted to keep it light. Since we are having a very fast-paced semester, I thought of removing that derivation. And that is quite an involved derivation. Okay, so this is IA11 by definition. Now let's go to IA12. IA12 is this. I'm not going to put body, the word body I will not put everywhere. It is implied that the integration is over the body. This is IA12. So this is the first scalar component, second scalar component here. IA13, what is IA13? You can probably guess by now. We have written enough on this slide to actually be able to write the exact expressions for all the other components. x1, x3, dm. x1, x3, dm. The next place is for IA21, right? 1, 1, 1, 2, 1, 3 I have written. What is IA21? IA21 is going to be x2, x1, dm. Next place is for IA22, and that is going to be x3 square plus x1 square dm. Next one is IA23, that is x2, x3 dm. IA31, x3, x1 dm. Finally, IA33 is x1, x2, x1 square, x2 square dm. One. The SI units of this all these scalar components is going to be kg meter square. Now note that this matrix, if you observe the various components, you will realize that this inertia matrix is a symmetric matrix. Symmetric matrix. It is a symmetric matrix. Which means what I'm trying to say is IA12 is equal to IA21, IA23 is equal to IA32, and IA31 is equal to IA13. That's clear. You see IA12, what is the definition? Minus x1 x2 dm. IA21 is what? Minus x2 x1 dm. But you write the product as x2 x1 or you write it as x1 x2. Doesn't matter. Scalars, the products of scalars, it doesn't matter which order various factors are appearing. So these are equal. Right? Similarly, you see IA23 minus x2 x3 dm, IA32 is minus x3 x2 dm. These are equal. Similarly, IA13 and IA31 are equal. So it is a symmetric matrix. The inertia matrix of a body at a point relative to a coordinate system is a symmetric matrix. The off-diagonal components. So in this matrix, there are three diagonal components. This is a diagonal component, DC. Write it here. Diagonal component, right? The elements or the numbers which are appearing on the diagonal of the matrix, we call them diagonal components. Diagonal components. Whereas these can be called off-diagonal components, OC. OC. Off-diagonal components. The diagonal components, which are IA11, IA22 and IA33, are also called moments of inertia. Moments of inertia of the RB at point A relative to the coordinate system of inertia. And this is a phrase you are already familiar with. Even in class 11, 12, they talk about moments of inertia. But then in class 11th and 12th, they don't talk anything beyond moments of inertia. You are only introduced to this idea of what I am calling as IA11 or IA22 and IA33. The off-diagonal components are not introduced in class 11th and 12th, but they are also important. The off-diagonal components are actually 6 of them. And these are called products of inertia. Products of inertia. Products of inertia of the RB at point A and relative to clearly there are only 3 independent products of inertia because the matrix is symmetric. only 3 of 6 products of inertia are independent. Okay. So these are the mathematical definitions. What is the physical meaning? Is there any physical meaning we can associate with these components, products of inertia and moments of inertia? Let me share with you what my understanding is about their physical meanings. So if I focus on IA11, remember its definition is this. What is the physical meaning? The physical meaning, first I will write a sentence and then I will explain that sentence further. It is the measure of how far the mass of RB is distributed from the x1 E1 axis. If I go back to this diagram, take a more regular shape, it will be easier to visualize the physical meaning. Let us consider this cylinder. This is the body. And the point A is here. Okay, x1 E1 is along the axis of the cylinder. X1 E1 is along the axis of the cylinder. So consider this RB with mass say 10 kg. Alright. Now suppose I use that same 10 kg of mass and create another cylinder which has a higher radius but a shorter length actually. Okay. Let's call the radius of this as R1 and radius of this as R2. And I'm saying R2 is more than R1. Same mass 10 kg. If you look at this definition, I hope you will be convinced by my statement that IA11 for case 2 will be more than IA11 for case 1. This is case 1 and this is case 2. You take the same amount of mass, you make a cylinder with smaller radius and longer length, then tomorrow you use the same amount of mass, same material, same shape, still a cylinder, but you make the radius larger and naturally the length will become shorter, And then you calculate IA11 for the two cylinders that you have created. IA11 for case 2 will be more than IA11 for case 1. Why? Because you are placing more DMs. Listen to my words. You are placing more DMs, small masses, at farther distances from the x1 even axis. In which case? In this case 2. And that is why IA11 for case 2 will be more than IA11 for case 1. So that is what I mean, that IA11 is a measure of how far the mass of RB is distributed. If you shrink all the mass of 10 kg on x1 even axis, that's possible. You make the length infinity of a cylinder, right? Spread the entire 10 kg of mass over an infinite length of the cylinder. What you will have? It will be a line distributed RB. I mean, the entire mass is distributed along the line. And guess what? IA11 in that case will be 0. 0 for case 3. Okay. So I hope with these 3 cases, you will find my statement reasonable, that IA11 is a measure of how far mass is distributed from x1 even axis. The farther it is distributed from the x1 even axis, and when I say farther from x1 even axis, I mean farther in these directions, in x2 e2 and x3 e3. The farther it is distributed, IA11 will be more. Okay. So based on this understanding, if I ask a question, I ask you to give me an English sentence explaining the meaning of IA22. What would be your response? Again, I would have liked to hear a response, but the communication is not very smooth, so I would raise this curiosity in your mind, that what would be the statement, and then answer it. I want you to think. I'll let you have 20 seconds. First, to at least think, how would you explain this in one single English sentence? What is IA22? And that sentence will start with similar words. Measure of how far the mass of the RB is distributed from what? Here it was from one axis, x1 even axis. So everything in my sentence will remain the same, only thing that will change is x1 even axis. So IA22, which is this, is indeed a measure of how far the RB mass is distributed from the x2 e2 axis. Similarly, IA33, I'm sure you can make a sentence if I ask you to, and if you yourself have this curiosity. And when I say how far, I am repeating, when I say how far, I only mean in this way. So if it is like x2 e2 axis is this, I mean far in this direction and in this direction. So this will be x1 e1, x2 e2 and x3 e3. This is what I am calling as far, in perpendicular direction to x1 e1. That's the meaning of the word far here. Okay. So IA33, I will not write the full sentence, but you can write something like that. How about the physical meaning of the products of inertia? Physical meaning of the products of inertia. Products of inertia. Will it be the same physical meaning? Doesn't look like. If you pay attention to a component, IA12 it has a very different quantity. I mean, they all of them are the members or the components of the same matrix. They are the scalar components of the same tensor IA. But if you pay attention to the definition of product of inertia, very different from, say, something like IA11, which was this. Mathematically, it's very different. Okay? And thus, its physical meaning would also be different. You cannot use something like this to explain the physical meaning. And there is also a minus sign. And mind you, x1 and x2 themselves can be negative. So x1 can be like this for different dms, I am saying, and this. Whereas whatever was appearing here, the whole thing was always greater than 0 or equal to 0. It was a positive definite quantity, this whole thing. Here it's not the case. Okay. So the way I explain the physical meaning of it is the following. Point A. IA12 is a measure of how the mass of RB is distributed in different quadrants of plane x1 e1, x2 e2 and the other planes which are parallel to x1 e1, x2 e2. Long sentence I need, and still I do not know whether it communicates all the meaning that I want to convey to you. This is my own attempt to explain it. You don't find an explanation like this in many books. At least I haven't come across any explanation in any book. They just give the expression and move on. This is my own attempt to explain it. It is a measure of how the mass of RB is distributed in different quadrants of the plane x1, e1, x2, e2 and the other planes which are parallel to x1, e1, x2, e2. Let me elaborate on this further, what I mean by this. Consider a thin body which is lying in x1, e1, x2, e2 plane, the way I have shown. Okay. Now consider this body to be of circular shape actually. Circular shape. We have the definition IA12 as minus x1, x2 dm. Now if you pay attention to this body, since A is the center of circular disc, every dm that you can locate Suppose you consider a small chunk of mass dm here, which has coordinates as x1 comma x2, or let me just call it a comma b. Okay, at a comma b there is a small chunk of mass dm. Now realize that since it is a body of since it's a circular disk, there will also be a mass dm, same amount of mass, and I'm saying that this is rho density is uniform for the disk. Every time you locate a dm with coordinates a comma b, you can locate another element of same mass but coordinates a comma minus b. Right? I hope you will agree. For every dm at a comma b, I can find another same amount of mass located at a comma minus b. What does it mean for this integral? It means that the contribution of this mass, where my cursor is, to this integral will be exactly cancelled out by the contribution of this mass to the same integral. Because once this will give you dm times what? A times b dm. Whereas this will come with minus, so this will come with minus ab dm, and then there will be minus in the beginning, a minus b dm. What happens? You get ab dm plus ab dm cancelled out. Okay, so if your IA12 is small means close to 0. Maybe I put the magnitude. It means that there is a sort of symmetry that is existing in the distribution of mass. How mass is distributed over the 4 quadrants, that has an implication on IA12. And here it doesn't matter whether the mass is at a shorter distance from any axis or it is at a larger distance from an axis. Here what matters is whether you can find a counterpart of dm in another quadrant which has the ability to cancel out the contribution from the first dm or not. Okay, so that is the tendency which is captured in IA12. Okay, and thus I make this statement. I am showing you a body which is completely concentrated on in the x1, e1, x2, e2 plane. But even if you have a 3-dimensional body, similar thing can be examined in different planes which are perpendicular to, or rather parallel to, the x1, e1, x2, e2 plane. Same thing will happen in various planes, and that is why I make the statement that IA12 is a measure of how the mass of RB is distributed in different quadrants of the plane x1, e1, x2, e2. Mind you, there is 1, 2 here and 1, 2 here, and other planes which are parallel to x1, e1, x2, e2. Okay. Now I will not say anything more than this, because I'm not even sure like whatever I have said you have been able to grasp it or not. So I will leave the matter here and encourage you to think more about it. And I believe if you think more about it, you will see the reason why I am making this statement. And as I said, this is the best that I can communicate as far as the physical meaning is concerned. Now, one thing I would still like to add, if IA12 has this physical meaning, and now if I ask you what is IA13, so if I have to say what is IA13, IA13 will be a measure of how the mass of RB is distributed in different quadrants of the plane x1 e1 and x3 e3. So if I talk about IA13, the planes will change. Sentence will remain the same. Wherever x1 e1 x2 e2 is coming, you will have to put x1 e1 x3 e3. Okay, that would be the physical meaning of IA13. And similarly IA23, you can attach a physical meaning. Okay. Now let's move to something which you are more familiar with. As far as the inertia tensor of an RB is concerned, there is a theorem called the perpendicular axis theorem. Perpendicular axis theorem, and we will write the statement of that and then we will quickly prove it. Again, this will be useful in solving problems. So what is the perpendicular axis theorem? I'll give a break, just let me have a couple of minutes, then we will have a break here. So I have a body of negligible thickness along x3 direction. So you have a body of negligible thickness. You can always put your coordinate system such that x3 e3 is the axis perpendicular to the plane of the body, right? This is M. M has negligible thickness. Along x3 e3 direction. As usual, A is fixed in M. The perpendicular axis theorem tells us this. To be very precise, this is approximately equal to IA11 plus IA22. That's the theorem. How does it help? It helps because for a thin body, if you know IA11 and you know IA22, at least for IA33, you do not have to do any integration. Remember, IA11, if one has to find, he will have to do this integration, right? And IA22 will be this integration. Two integrations you have done, and then you want to know IA33. You can just add IA11, IA22 to get IA33 if the body has negligible thickness. That's the perpendicular axis theorem, and that is the utility of that. If you do not want to use perpendicular axis theorem, nobody is stopping you to do this. Go ahead and try this integration also. That is also fine. But if you want to save your effort, don't want to do this integration, use this theorem. Let me quickly prove it and then we take a break. So what's the proof? The proof is very simple. I start with IA11, the definition I have already written. x2 square plus x3 square dm. I'm going to approximately write it as x2 square dm, right? Because x3 is very small, the body has negligible thickness. IA22 by definition is this, and again the body is negligible, so this is approximately x1 square dm, right? Add this side of these two equations, get IA11 and IA22, and then you add whatever is on this side, and what we have is x2 square plus x1 square dm, and this indeed is the definition of IA33. Just two lines are required to prove this. 3, 3, 1, 2, 1, 1. Use it as whenever applicable, but keep this in mind. Only when this condition is there, it would be accurate enough. Let's take a break. We meet at 5. Meet at 5:15. We meet 5:15. We will meet. 9 minutes break.